Well, good morning, everyone, in all your various locations. Mother Nature certainly has teed up this topic nicely for us this morning. We were surprised with 10 inches of snow last night on top of, just mountains that we've already had this winter here in southeastern Massachusetts. It's certainly going to be one of the winters that we tell our grandchildren about, I think. So today I'm going to be telling you about some of the recent work that I've been doing with my colleague Steve Vavris at the University of Wisconsin, where we've been looking at this question of particularly how the Arctic change is affecting weather patterns down here in mid-latitudes where we all live. I'll broaden that out a little bit in the beginning just to talk about climate change in general and how that's affecting weather. So we'll get kind of a background on sort of the state of this topic. So this is probably a familiar scene to a lot of you who live in the East. It's really, as I said, just been an absolutely amazing winter. And I've been getting a lot of complaints. In fact, I'm starting to worry about goats showing up in my driveway, perhaps. A friend of mine sent me this cartoon that you're looking at now, and I think it kind of sums up the attitudes of people around here right now. But we don't have to go back very far in time to see a very different story. In fact, the winter of 2012, only a couple of years ago, was pretty much the opposite of what we're seeing this winter and last winter both, where we had, instead of record cold temperatures in the east, we had record warm temperatures. In fact, we broke about over 3,000 high temperature records that winter. So just keep that in mind. And we'll talk about that some more in a little bit. So the extreme weather that's been happening around the U.S. and Canada is not in isolation. We're actually seeing extreme weather events all around the Northern Hemisphere. In the UK, for example, for the last couple of winters, they've been absolutely pounded by storm after storm. Last winter, they broke their precipitation record for the winter. And that record goes back 250 years. So breaking that record is a very big deal. And in places like Japan, northern Japan, where they already get a lot of snow, they've seen some really extraordinary snowfalls. So just looking at this picture, it's really hard to imagine what the snowplow looks like that keeps this road clear. So we actually know that these types of extreme weather events are increasing. And it's really, some of the information actually is coming from your community. And you know about this better than most because it really affects your bottom line. So here's just one example of some of the information that's been put out, in this case from Munich RE, and I like this plot, this graph, because it compares the time series of extreme events that are related to things like geophysical changes, so earthquakes and tsunamis and volcanoes. Those are shown in the red bars starting in the 1980s and going into the present day. And the other three bars are all related to weather. So the green bars here are storm-related extreme events. The blue are related to water, so flooding and landslides, mudslides rather. And the orange bars there are more climate-related, so extreme temperature events and droughts, forest fires, that sort of thing. And what we notice is that the geophysical events in red are not changing in time, which is what we'd expect, but the others are increasing in time. So we're seeing an uptick in the extreme events related to weather. So people really are noticing that their weather they're experiencing in their own backyards is really changing. They watch the news and they see stories about extreme events happening all around the globe. And they're really starting to worry or to talk about and wonder what the heck is going on. But even more particularly, they're really starting to ask now, is this somehow related to human-caused climate change? So this question has been around for quite a while. Scientists have been a little bit wary of answering this question either way, because traditionally we've kind of separated weather issues from climate issues. Over the last 5 or so years, it's become increasingly clear through many, many studies that we can connect what's happening in the climate system with changes in weather patterns. So more and more of us now are very comfortable answering this question with a pretty resounding yes. So just to step back a little bit, I'm sure many of you are familiar with graphs like this that show how the Earth's temperature has changed over the distant past. So in this case, we're looking at the red curve there is how the Earth's temperature has changed starting about 450,000 years ago, so going way back in time. And we see that there are big swings in temperature over this time period. There are glacial or ice ages, which is when the temperature was low by several degrees, and then there are other periods where we were in interglacial periods where it was warm. And we know what causes these fluctuations in temperature in the past. We know it's due to variations in the Earth's orbit. The Earth's orbit is not constant. Sometimes it's more circular, sometimes it's more elliptical. And we also know that these temperature changes are affected by changes in the Earth's tilt relative to its orbit around the sun. Both of these affect how solar energy is distributed around the Earth. And what you also see on here is the blue curve is showing how much carbon dioxide there was in the atmosphere along with the temperature. And we see that they're very closely related. When the temperature is high, the carbon dioxide levels are high. But if you look way off to the right of this graph here, you see that what's happening with the carbon dioxide is now completely out of sync with what's going on with the temperature. And there I've shown the level of carbon dioxide that we have in the atmosphere right now. And we know that it's higher now than it's been in at least 800,000 years. And probably even longer than that, something on the order of 2.5 million years. And as I said, the temperature really hasn't caught up with this yet. And that's because we've put this carbon dioxide into the atmosphere so fast that the Earth's system just hasn't been able to equilibrate yet. So we're completely out of whack with the amount of carbon dioxide in the atmosphere. And of course, we know where that carbon dioxide is coming from. It's coming from burning of fossil fuels. But we also know that the last time the carbon dioxide levels were this high in the atmosphere, the globe was a very different place. It was several degrees warmer, and sea levels were tens of feet higher. So this is where we're headed, unfortunately. Now, we do see that the Earth's temperature is starting to respond to this very rapid increase in the amount of both carbon dioxide and other greenhouse gases in the atmosphere. This plot here is going back only 1,000 years now, looking at how the Earth's temperature relative to an average has been changing over time. And what you see is that starting from 1,000 years ago, coming towards present, we were actually in a cooling phase. So we were coming off of one of these warm events that's related to changes in the Earth's orbit, and we were actually cooling off. But in the red part of this graph here, in recent years, you see that the Earth's temperature is, in fact, rapidly increasing, and we know why that is. It's responding to this very high level of carbon dioxide. And, in fact, the warmest 19 years on record have all occurred in the last 20 years. We also know that this warming is not happening evenly around the globe. So if we look at the departures from normal in the globe's temperature over the last decade, which is in the bottom right there, what we see is that basically the colors, the yellows and reds and oranges, are all telling us that the Earth is warming, but you notice that in the far north is where the warming is the fastest, so up in the Arctic. And we're going to talk a lot more about this. But just another little factoid here, January 2015, this past January, and we could add February 2015 onto this now too, this period was, these months were now the 360th consecutive month that's been warmer than the 20th century average. So if you're younger than 30 years old, you have never lived in a month that was cooler than average. It's really quite a different world that we're living in now. So a question that often comes up is, well, how do we know that humans are responsible for this warming? Well, there's a lot of ways that we can tell, but probably one of the easiest ones to explain is to look at this tool that we use and you hear a lot about are these global climate models. So these are very sophisticated computer programs that use math to simulate all of the physics that happens in the climate system, or most of it at least. So we can simulate storms, we simulate precipitation patterns, ocean currents, winds, even some of these models even have vegetation in them. So they're very, very complicated models. And we can use these models to look at how the Earth's climate system has changed and will change. So if we use one of these models to simulate what's happened to the Earth's temperature in the last several decades, so in this case going back to 1900, the black line here is what the temperature of the real world did over this time period. And the blue line here is what the model has simulated. Now, we've only told this model about the natural changes in the climate system, things that happen naturally. So things like the change in the amount of energy we get from the sun, for example, and volcanic eruptions that have happened in the past. And this seems to work quite well. The model does a good job of simulating the real world up until 1960. But after that, the model and the real world diverge. And of course, we know why that is. It's because we haven't told the model about the fact that greenhouse gases have been increasing so rapidly in the atmosphere. And this bottom plot here shows what the model simulates when you do tell it about the increasing greenhouse gases. And you can see that it now matches very well with the real world, which again is in black. So not only is the atmosphere getting warmer, but it's also gaining water vapor. And this is important for a number of reasons. The water vapor in the atmosphere has increased by about 7% since the 1970s or so. This water vapor is really critical because it not only is a greenhouse gas, so it augments the warming that we're getting from the other greenhouse gases that are also increasing, but also that water vapor is one of the main sources of energy that fuels storms. So the more water vapor we have in the atmosphere, the stronger the storms are apt to be. We know this is especially true with hurricanes. And of course, that water vapor is also moisture that increases the amount of precipitation that happens in any storm. And so what the plot on the bottom here is showing is the change in the frequency of very heavy precipitation events across the United States. I'm sorry I don't have this data for Canada, for those of you who are in Canada, but it's a similar story for you. What we see is that there's a big increase in the frequency of these very heavy precipitation events, especially in the eastern part of North America. And this is because of this increase in water vapor in the atmosphere. So let's move to the Arctic now and talk about how the Arctic has been changing over the last several decades. And I'm sure you're all aware that the amount of sea ice in the Arctic has been declining. We can look at this by starting with a satellite image going back to 1980. So this is from September, the middle of September 1980. And we show September because that's about when the sea ice melts back to its smallest aerial coverage every year. So we're looking down on the North Pole here. You can see Greenland and Canada on the left. The pink stuff there is all sea ice floating on the Arctic Ocean. And you can see that back in 1980, this was typical. In the summer, the sea ice pretty much filled up the entire Arctic Ocean. So fast forward to 2012, and we look down at the same scene, and we see something very, very different. So now you notice that the sea ice covers much smaller area in the Arctic Ocean. In fact, in 2012, it was about half as big in terms of area as it was only 30 years ago. And if we multiply that aerial coverage by the thickness of the ice, we get the volume. The volume of the sea ice in the Arctic in 2012 was 3/4 smaller than it was only 30 years before. So this is just a tremendous change. And you can see by looking at the colors in these two images side by side that they're quite different now than they were back then. And that's telling us that the ice that's left is very thin, it's very broken. People who go up there to study it call it rotten and slushy. So it's very vulnerable to shifts in the wind and anomalous ocean currents and anything that might affect it. So it's a very vulnerable ice cover now. So you might be thinking, well, okay, so that's only 30 years. Climate has been changing for a long time. How do we know this is something really unusual? Well, we can actually go back with quite a bit of confidence about 1,500 years and look at how much sea ice there was in the summertime. This is information that's been extracted from the sediments at the bottom of the Arctic. So different plankton live in the water column depending on whether there's ice on top of them or not. And by looking at those different plankton that have settled in the mud, they can determine how much ice there was. So what you see going back 1,500 years or so is that there were a lot of wiggles from year to year and even decadal changes, but it was pretty steady overall until you get to the right-hand side of this graph. And this blue line here is the modern record. And you can see that we're now in a very different place than any time during the last 1,500 years. But this graph doesn't even have that record year of 2012 on it. And if we do put 2012 on there, it doesn't even fit on this graph. So I have a little animation here of the sea ice in the Arctic that just kind of helps give you a feel for how sea ice behaves in the Arctic. So let me blow this up big. And we'll let it rotate up here to the Arctic, and you can see the different land areas that are marked there. So let me just explain now what you're going to see here. So here's Alaska, the north part of Canada, and Greenland. So these white and blue colors here filling the Arctic Ocean are, of course, sea ice. The colors refer to or correspond to the age of the ice that's in any given location. The white ice is the oldest ice, and the dark blue is the youngest ice. So it turns out that the age of the ice is pretty closely related to how thick it is. So you can think of the white ice as being very old, thick ice, and the blue is very young, thin ice. So when I put this animation in motion, what you're going to see is a couple things. You're going to see the seasonal changes of the ice. So every winter it's going to grow and fill up the whole Arctic Ocean, and it'll melt back in the summer to its smallest extent. You'll also see a tendency for the ice to circulate in a clockwise direction, generally, through the Arctic Ocean. And this is in response to the average winds that occur up there, the polar easterlies. So let's put it in motion. And you can see the time here on the bottom left. We're starting in the late 1980s. And I should mention that the way this ice age is determined is using satellite images. They identify features in the ice and then track those features over time and just keep track of how long they've been there. So as we come up now into the mid-1990s, you can see the ice generally rotating in a clockwise direction, and eventually that ice makes its way out into the Atlantic where it eventually melts. As we're getting now into the mid-2000s, you can see a pretty marked change in the colors of this ice that's left. You can see that there's very little of the white ice left. The oldest, thickest ice is disappearing. And as we get right up to present here, you can see where we are now compared to where we started, where much, much less of the old thick ice than there used to be only a couple of decades ago. So why do we care about this ice up there? Well, as you know, ice is very white, and it actually is so white that it reflects almost all of the sun's energy that hits it. And in this image here, I'm showing what the ice looked like in 2012 compared to the average over this period from 1979 to 2000. So if we have much less ice there in the Arctic Ocean, then that means that much more of the sun's energy is going to go into the climate system, not be reflected to outer space. It's going to go into the ocean, it's going to warm the ocean, and it's responsible for the Arctic being 2 to 3 times, the Arctic is warming 2 to 3 times faster than the rest of the globe. This loss of ice and also the loss of snow in the spring on the land areas are both major contributors to this rapid Arctic warming. And we can see this warming very clearly in this plot of how the temperature departures from average for the Arctic, which is in the turquoise, over time, going back to the late 1940s, compares to the changes in temperatures in middle latitudes, which is where we all live. You can see that it has been warming in our area, but nowhere near as fast as the warming that's been happening in the Arctic. And we call this rapid Arctic warming Arctic amplification. So it's an amplification of the warming that's happening in a global sense. Now, one of our challenges in trying to understand how this rapid Arctic warming is affecting things like weather patterns is that the signal of Arctic amplification really only started about 15 years ago, maybe 20 years ago. And that represents a real challenge because it's not very many years to try to extract a statistically significant response from changes in the atmosphere. So just keep that in mind as we continue along here. So let's talk about why this Arctic warming is so important, in particular how it relates to the jet stream. So if we think about a layer of air that extends from, say, somewhere in the mid-latitudes, let's just pick, say, New York, for example, all the way up to the Arctic. We know that air expands when it warms, so this layer of air is going to be thicker over New York than it is over the Arctic. And this difference in thickness of the layer of air creates really kind of a hill in the atmosphere. You can think of sitting up on top of this layer of air. If you were looking towards the north, it would be like you were looking down a hill. So air sitting on top of this hill wants to flow down that hill just like water wants to flow down the side of a mountain. So it starts to flow northward. It creates a wind. And because the Earth is spinning, that wind gets turned to the right, and it becomes what we call the jet stream. The jet stream is this very fast-moving river of air high over our heads, up where the jets fly, and it pretty much encircles the entire northern hemisphere. So now let's go back to this concept of Arctic amplification. The Arctic is warming much faster. So that means the layer in the Arctic is getting thicker, much faster than it is down here in New York, where it's not warming as fast. And so this is having the effect of making this hill less steep. And when the hill is less steep, there's less force to drive the jet stream. And so as a result, the winds of the jet stream weaken. And this is something that we can measure, and that's what's being shown here. This black line here is showing how the west to east winds of the jet stream have changed going back to the late 1970s to 2012, and we see that there's been about a 10% decrease, and this is for the fall. Also on here, we see a dashed line showing how sea ice has changed at the same time. And you can see that the winds have really started to decrease right about when the sea ice really started to decrease. Now, meteorologists know that, or they've observed over many decades, that when the jet stream is in a weak period, that it tends to take a wavier path as it travels around the northern hemisphere. And these waves that I'm talking about are in the north-south direction. So the jet stream tends to flow north and then south in this wavy pattern around the northern hemisphere. So a little way to remember that is with this sort of tongue twister here. Weaker westerly wind is wavier. These little animations here show you why we care about these waves in the jet stream, or one of the reasons, and why the size of them matters. So when we have small waves, like in the upper panel here, we see that they move quite quickly from west to east across the land underneath. But when they get bigger, which we expect to happen as the jet stream weakens, they move much more slowly across the land. Well, why is that important? Well, turns out these waves are absolutely critical to the weather that we experience down here on the surface. And this schematic is of a jet stream. So the orange line going across with these waves in it is a schematic of the jet stream. It's where the winds are really strong. It tends to blow from west to east. And you can see right off the bat that the jet stream separates the cold air to the north from the warm air to the south. So when the jet stream is north of you, you're in the warm air. And when it's south of you, you're in the cold air. The other thing to notice is that these waves in the jet stream are what create the dynamics in the atmosphere that create the storms, and they create the high pressure areas that bring us our good weather. So in this part of the wave where the winds are coming from the southwest is where we tend to get the stormy periods. So think maybe you're familiar with what the pattern's been like this winter along the east coast of North America, but we've basically been in this part of the wave in the jet stream all winter long, and that's why we've had such a snowy winter, especially in New England. But in this part of the wave, where the winds are from the northwest, is where you find the high pressure areas, the dry high pressure. So where you are relative to one of these waves in the jet stream has everything to do with the weather that you experience at the surface. So this all looks very neat and tidy and pretty easy to understand, but now I want to show you what the real jet stream looks like, and you'll see that it's actually not tidy at all. So this is an animation that was created by NASA's Science Visualization Studio. It's of real winds in the upper atmosphere. It spans about 2 to 3 weeks, something like that. And the yellow and red colors are showing you where the winds are strongest, so you can easily pick out where the jet stream is. And there are a couple things I want you to notice as we move through this animation again. First of all, I want you to notice just what a messy atmosphere we're dealing with here, that there's waves of all different sizes, and we have swirls, and just it's really quite a complicated and chaotic system. The other thing I want you to notice is that there are times, like the one I've frozen here, where these waves in the jet stream are relatively small. Think back to those simple animations that I showed you a couple minutes ago. And when these waves are small, you see they tend to move quite quickly across the continent. But then there are times when the waves get really large. And when I put it in motion again, what you'll notice is that these waves move very slowly across the continent. Now think back to what I just told you about how the weather corresponds to these waves. So if these waves are moving very slowly, that means that the weather they create, whether you're in the stormy pattern or whether you're in the high pressure pattern, are going to change much more slowly. It's going to feel like your weather is very persistent. And, this winter has been an incredibly good example of a very persistent weather pattern. So this is the idea behind the connection to the Arctic. So the research that we're doing is really homing in on this question about whether the jet stream is actually getting wavier or not, and whether we can connect any changes in waviness that we do see back to the warming of the Arctic. So this is really where the research is the rubber's meeting the road in terms of this research topic, and it's a relatively new field of research. We've only been studying it for the last couple years. This hypothesis that we came up with that connects the rapidly warming Arctic to changes in the jet stream was just published in 2012. So this is very new stuff, and it's certainly all the questions have not been answered, and there are a lot of people now focused on this topic all around the world right now. So let me just give you a little taste for one of the ways that we're trying to figure out whether the jet stream really is getting wavier or not. We can think of, or we can look at the atmosphere like you would look at a topographic map of the Earth. So if you were going hiking, you would use a topographic map to show you where the mountains were, where the valleys were, and these lines on a topographic map are lines of equal elevation, so that you know that if you walk along one of these lines, that you won't be going up or down, you'll be staying at a constant elevation. So we can use the same concept to map that layer of the atmosphere that I was describing before, which is thicker where it's warm and thinner where it's cold. So as we look down on the North Pole here and down over North America, we see that, as you'd expect, that this layer of atmosphere is much thicker down in the tropics where the air is very warm, and it's much thinner over the Arctic where, of course, the air is very cold. So the other thing we can notice is where these lines are very close together, just like on a topographic map of the Earth, we know that's where the hill or the slope of the land is very, very steep. And this is where we, in fact, find the jet stream as well, because that very, very steep slope of this layer of the atmosphere creates the strong force that drives the jet stream. So we can take these lines of equal elevation and actually track their shape. And as you can see, if you pick one of these lines, it follows the jet stream, and you can see the waves in the jet stream. This is just for one particular day. So we can do this for every single day. We can measure these waves and look at how they're changing over time. And what we notice is that if we look at particular extreme events that are related to very persistent weather patterns. Here's an example of some unprecedented flooding that happened in Spain back in September of 2012. Here's Spain right here in the bottom middle of this plot. And again, we're looking at one of these topographic maps of the atmosphere. We can follow the jet stream, and we see that it's in one of these very, very wavy patterns, and Spain is right in that stormy part of the wave. And because the waves were so big in this case, they were also very, very slow moving, which led to the persistent stormy pattern that Spain experienced at this time that led to the very terrible flooding that they had. Another example is last winter over North America, and this was an event called the Attack of the Polar Vortex, which I'm sure you all remember. And again, we see that there's a very wavy pattern to the jet stream with a big, what we call a ridge, these northward swings in the jet stream over the west, which led to California and much of the coast of BC and Alaska having one of the warmest winters they've ever had, while we in the east suffered under pretty severe cold and a lot of storminess along the east coast. But the key here is that, again, this wave is very, very big. The pattern was extremely persistent. So getting back to our measurement of these waves, we use a very, very simple idea, and that is to just pick one of these lines of equal elevation and basically just measure how far north it goes and how far south it goes every single day, and look for cases when this difference in latitude exceeds 35 degrees. And when it does that, we call it a high amplitude pattern. So we basically just count up these high amplitude patterns over the different seasons, over different regions, and we can track whether they're increasing in frequency or not. So if we take a look at some of the results from this, really simple metric, but, when you've got a situation like that chaotic atmosphere that I showed you in the animation, simple metrics are good. At least that's my philosophy. So what I'm looking at here now is a plot of the frequency of these high amplitude patterns shown in green here, going back to the late 1970s. So this green curve here is clearly increasing as we go through time up to near present. And that's telling us that these very wavy jet stream patterns are increasing in frequency. Again, this is for fall, over the whole northern hemisphere. Also plotted on here is how the winds have been changing over this time. And as you see, they've been decreasing while the frequency of these high amplitude patterns have been increasing. And we can focus in on the North Atlantic just to show you one particular region. And again, we see a very strong uptick in the frequencies of these high amplitude patterns, along with a very strong decrease in the speed of the upper level westerly winds. And we can look at this all around the Northern Hemisphere, and that's what's shown in this table. We've broken the Northern Hemisphere into these various regions and into all 4 seasons. So this is January, February, March, April, May, June, etc. The colors here are showing you where the increases in these high amplitude patterns have been the largest. So these numbers here are percentage changes during the recent couple of decades versus the early part of the record. So in the Atlantic, for example, in the fall, we've seen almost a 50% increase in the frequency of these high amplitude patterns. Fall stands out as having the biggest changes, which is what we expect because that's in response to the loss of sea ice that we've observed in the summertime. But we also see other seasons are also showing increases, especially in the summer in the Atlantic and North America region, but in the winter as well. All right, so wrapping up towards the end here, I wanted to take a look at some more particular extreme weather events and see how the jet stream looks when those were occurring. So again, we'll go back to this winter just a couple of years ago when the situation was very different from the one that we're experiencing this year. And we're looking at the differences in the surface temperatures from what normally looks like, and we see this huge area with very, very warm temperatures during March of 2012. Compare that to the first 2 weeks of this past February, and we see basically just the opposite pattern. We see this huge area of temperatures that have been much colder than normal in the east, but out west, they've been experiencing one of the warmest and driest winters they've ever had. So you can probably imagine, now that I've told you so much about the jet stream, what it looked like in these 2 very different scenarios. In March of 2012, we had this big ridge over the east, and that allowed all the warm air from the tropics to penetrate way far north, whereas over the west, the jet stream was dipping southward, and they were in much cooler air than they would normally see. But in this past winter, and also last winter, the pattern was almost identical in both these past winters. And what we see is just the opposite of what was going on in 2012, where we had this huge ridge parked over the west, allowing all the warm air and preventing all the storms from entering California. And we see this big trough or dip in the jet stream over us that's allowed all the cold air from the Arctic to penetrate farther south. And again, here we have this stormy part of the wave creating all the nor'easters and snowstorms that have hit all along the eastern seaboard. So let's step back a little bit and look at what the jet stream looked like last winter all around the northern hemisphere. So here's North America down in the bottom middle. Again, you see this big ridge over the west and dip southward trough over the east. The colors here are telling you about the temperature anomalies or the differences from average of the temperature in various regions. And as we walk around the whole northern hemisphere, we see this big trough also over the UK, which, remember what I said in the beginning, how the UK last winter had the wettest winter in their entire history because of this big trough. You remember the Sochi Olympics in this area where they were having trouble keeping snow on the ski slopes. And this white outline here is just showing you basically the core of the jet stream and reinforcing this idea that it was just an incredibly wavy jet stream pattern. So fast forward to this year, and, it really looks awfully similar. This big ridge over the west, big trough over the east, a lot of warming in Scandinavia. So this pattern has actually been so persistent that if you look at the differences in temperature from normal for the entire year of 2014, you can see this pattern is very clear in these temperatures where it's very warm over the west, cold over the east, warm over Scandinavia, and this is over the entire year. This pattern has been extremely persistent. And we're just starting to learn why this is happening. Just in the last couple of weeks, there's been new research that's come out looking at why we're seeing this incredibly persistent pattern. And there are basically 2 parts to the story. The first part is this pattern of sea surface temperatures out in the Pacific Ocean that's called the Pacific Decadal Oscillation. It's called decadal because it has two phases to it, the positive phase and the negative phase, that tend to shift from one to the other over periods of about 10 years. So up until late 2013, about 10 years before that, we were in the negative phase. So you can see these cooler than average temperatures in the Pacific Ocean off of the west coast of North America, with warm temperatures over in the western North Pacific. But in late 2013, in December or so 2013, it pretty abruptly shifted over to the positive phase, which now means we have these very warm temperatures along the west coast of North America. This pattern is known to be to correspond with the pattern in the jet stream that we've seen last winter and this winter. That is this ridge over the west and dip over the eastern part of North America. But what this new research showed was that if you combine this shift in the pattern and also take into account what's been happening with Arctic sea ice, in fact, that it's been disappearing so rapidly, the loss of Arctic sea ice has made this pattern that we expect to see in the positive phase, the PDO, even more accentuated. It amplifies it. And as you now know, when you amplify these waves in the jet stream and they get bigger, then they're going to become more persistent. So the combination of these two things is leading to this very persistent configuration of the jet stream that we've seen most of this winter, going back to last winter. So just to summarize, we know the Arctic is warming really fast. These red colors here are showing you how the thickness of that layer of atmosphere that I've been talking about has changed over the last decade. Over the Arctic, you can see it's much, much thicker than, the changes are much larger over the Arctic than they are down here in mid-latitudes. Here's Europe down here in the bottom. We see that this causes a weakening of the upper level winds. This is very basic atmospheric dynamics theory. When you reduce this difference in temperature between the north and the south, you expect to see a weakening of the winds because of that hill in the atmosphere that I was describing getting less steep. Now we think, our hypothesis says, that if you weaken those winds of the jet stream, we should start to see a wavier jet stream. And if that's the case, we know that leads to some pretty unusual and very persistent weather patterns. And when those patterns get very persistent, we tend to see certain types of extreme events happening which are related to very persistent weather patterns. Now, one of the other areas of research related to this connection here has to do with the fact that we know that there are a lot of other changes happening in the climate system simultaneously. And separating those influences and understanding the role of the Arctic warming, for example, compared to changes in ocean temperatures in different regions of the world, how those things are influencing the jet stream individually and perhaps together is a very hot topic of research right now, and that's one thing that a lot of people are working on. So, just in conclusion then, I want to thank you for this opportunity to talk to you all, and I look forward to your questions. So I'm going to unmute my phone now. The conference has been unmuted.
So if anybody would like to ask a question over the line, please feel free to do so.
This is Mark Baker. Hello? Yeah, this is Mark Baker. I was noticing that it was getting a lot colder, or somewhat colder at some point around Hudson's Bay and James Bay, and you were getting sea ice issues. Now, would this increase or reduce the sea ice, or just change the distribution?
Well, it varies from year to year. If you look at the sea ice in Hudson Bay in 2012, that very warm winter, then there was a lot less ice there. But of course, the last two winters, the ice has been quite extensive. So the ice there in that particular region responds to what's happening with the jet stream and the atmospheric temperatures that go along with it. So, the overall change in the Arctic is for the sea ice to be disappearing, but there are certainly areas where in any given year there might be more or less ice than normal. I see there's a question on the chat that says, will changes in the jet stream affect only long-duration weather patterns, or will it affect short-term extremes, short-duration extreme rainfall events as well? Well, that's a great question. It's very difficult to take a short-duration weather pattern, and by short, I'd say like on the order of a week or so, and connect it to any one particular influence or cause. So it's much harder to make that link back to short duration patterns, and where our focus is more on the statistical shift in the distribution of weather patterns, and that's really how this linkage between climate change and weather is moving forward, because it is so difficult to connect any one event back to any one particular cause. Okay, there's another question. Is there any known natural cyclicality, I'll get it, in the jet stream? Absolutely. And it goes back to things like that decadal oscillation, that Pacific decadal oscillation I was talking about, and El Niños. And there's also different sea surface temperature patterns happening in the Atlantic. All of those things affect the jet stream. They all shift on different timescales. So in the case of that Pacific decadal oscillation, that tends to fluctuate over a 10-year-ish period. But things like El Nino is a much shorter timescale period, so on the order of a year or maybe two sometimes. So the jet stream responds to all of those things. And as I said, it's really one of the things we're really working on is figuring out how those different influences are affecting it at any given time. Could you comment on ice conditions in Antarctica? Is it changing? If so, are these changes affecting climate weather conditions in temperate regions? This is a great question. And first I have to point out that, as you probably all know, Antarctica is a very, very different geographic region than the Arctic. The Arctic is an ocean. Antarctica is a continent. Antarctica is covered by a couple of miles of ice, and it's much, much colder in Antarctica, whereas the Arctic is very close to the melting point. And so if you change the temperature in the Arctic just a couple of degrees, it has a much bigger influence because you can melt a lot of ice. Whereas in Antarctica, because it's so cold, if you change the temperature just a couple of degrees, it really doesn't do much. That said, we are seeing some big changes in Antarctica as well. They are happening for different reasons. There is sea ice that forms around the continent of Antarctica every winter, but pretty much every summer that ice melts all the way back to the coast. So we don't have this opportunity to absorb extra sun's energy into the ocean like we have in the Arctic, and as in the case of the Arctic, where it's creating this, what we call a positive feedback, where it melts more ice, which allows more energy to be absorbed, which makes this vicious cycle. That doesn't happen anywhere near to this degree in Antarctica because that ice does melt back to the coast every winter. But what is happening in Antarctica, it's very complicated, but one of the things that's occurring is that the recovery of the ozone hole is actually causing the upper levels of the atmosphere over Antarctica to cool. So if you think back to this idea of the hill in the atmosphere, if you cool the upper levels of the atmosphere over Antarctica, you're actually making that hill steeper. And we're seeing the jet stream around Antarctica get stronger, and it's contracting closer to Antarctica as well. And this is affecting some of the temperate regions, and we think that for example, we know that the droughts in Australia are becoming more severe. We're seeing drought in South America as well. And it's partly related to this contraction of the jet stream southward. And so the storms just aren't making it as far north as they typically would. And so they're just not getting the fronts that would bring the rain. Okay, another question. What are the global models saying about when the Arctic will be ice-free in September, decades away? Well, yeah, I think, the consensus is sort of zeroing in around, say, 20 to 30 years, something like that, for when we're likely to see a mostly ice-free Arctic summer. I think we'll probably have ice banked up against the Canadian archipelago for quite a while, but effectively the Arctic is probably going to become ice-free within the next, say, 30 years, and I think most people agree on that time frame. I should mention that this, right as we speak, the sea ice in the Arctic is approaching record low levels, and it's looking like this winter we may set a new record for the least amount of ice for any winter we've seen. And that's still evolving. It can still rebound a little bit, but we're getting close to the date when we're apt to see the largest extent of sea ice in the Arctic. But it's been running along record low levels pretty much all winter long. Okay. Is there a voice question before I answer this next chat question? Okay, I'll just keep going. This next one is, what are the implications with respect to North Atlantic hurricane frequency? It's been quiet the last few years. Is this related to sea ice jet stream changes? I'm not a hurricane expert, but this whole climate system is connected. The fact that we haven't had hurricanes hitting, say, the east coast of North America much these last couple of years doesn't mean it's actually been quiet. It's just that their tracks have not taken them into the coast very often. I believe it was last year we had an above average year, or maybe it was the year before. But there isn't generally an observed change in the frequency of hurricanes, but what we do expect to see is a change in the intensity of hurricanes. Part of that is due to the warming oceans. Part of it is due to that increased water vapor in the atmosphere that I talked about, providing more fuel to tropical storms. So I think the hurricane experts are seeing evidence for an uptick in the intensity of hurricanes, but there isn't an expectation for an increased frequency. Okay, does melting Arctic ice change salinity in the ocean? And if yes, what effect does this have? It does affect the salinity, and not only is the melting sea ice changing that, but it's also the melting ice caps. So Greenland, for example, the melting of glaciers all around the globe, but most of them are in the northern hemisphere. And also we're seeing an increase in the outflow from rivers that flow into the Arctic Ocean. So the surface layer of the Arctic Ocean is becoming fresher. That has been observed. And as that fresher water makes its way out into the North Atlantic, you might remember the movie Day After Tomorrow. Their sort of premise was that all this fresh water was going to shut down the Gulf Stream and cause Europe and New York to freeze. Well, that's not how it works. That extra fresh water that comes out of the Arctic into the North Atlantic gets pushed to the right. And again, it's because the Earth is spinning. Anything that moves in the northern hemisphere gets turned to the right, and that includes currents in the ocean. And so that fresh water actually hugs the coast of Greenland. It goes all the way down the tip of Greenland towards the west and enters the Labrador Sea. And so it never really makes it out into the larger North Atlantic where it might affect something like the Gulf Stream. But overall, we're seeing that the warming of the oceans is overwhelming any impact of freshening. So we don't expect to see a big impact of that fresher water on the larger scale system.
Okay, I'm Glenn McGilvery at ICLR. I think we'll leave it at that. I want to thank Dr. Francis for I think, fantastic presentation. I knew she was going to do a great job, and she proved me correct, so that's fantastic.
Well,
please join us on April 18th for earthquake and May 15th for wildfire. And within a few days, we'll have a replay of this session on our YouTube channel. Thank you, everybody. Thank you, Jennifer.
You're welcome.
Take care.